fractional distillation. What is this fractional distillation technique is, what for we use it, and for different kinds of solution, fractional distillation, how would we carry it out, and also here we discuss about the graphs for fraction of liquid that is separated by fractional distillation at different temperatures in different types of mixtures is what we discuss. Now, first of all, fractional distillation. First of all, what is distillation? Distillation is a process in which first a liquid is evaporated and then condensed back to the same liquid. So, what is this distillation is? First of all, if you have a liquid, then the liquid is evaporated on heating, then the vapors that are formed are sent through a tube, glass tube, which is these vapors. Here this is an outer tube in which water is circulated, and then this is vapors condensed here, this is liquid, this is vapor, the vapor is condensed, and here again you will get back liquid. This is what is the simple distillation technique is. First liquid is evaporated, those vapors are condensed, and again you will get the liquid. What is the use of converting this liquid again to liquid? Why do we carry this procedure? So that what happens in this process is a less volatile impurity, whatever is present in the liquid. The basic purpose of you are doing this distillation is to remove less volatile impurities from the liquid. So, here what happens when the liquid evaporated at a particular temperature, that is what we call boiling point. The liquid evaporates at its boiling point, boiling starts, but those impurities that are present in the liquid which are having lesser boiling point, higher boiling point, then they will remain in this, the impurities will remain over here. These are all the impurities, suppose, then the impurities will remain over here. Pure liquid is what we get it, and the natural distillation process is involved in rain. The mechanism involved in the rain is, as all of us know very well, water from the lake, river or any water body gets evaporated, the vapors are formed, and as you know, at the upper atmosphere these vapors will collected and a thick cloud will be formed. At an appropriate pressure, the thick cloud condenses back into water. So, the same water that is present in the surface of the earth evaporated, again condensed back to the liquid, again we are getting the same liquid. Now, what happens in this process? As the water gets evaporated, the impurities will remain, the impurities which are having more boiling point than water at different stages, they will remain back, and only pure water will evaporated and then it gets condensed back. So, this mechanism involved in the rain, formation of rain or the occurrence of rain is the best natural example of distillation. Then what is a fractional distillation? Fractional distillation is repetition of the process of distillation for large number of times. For n number of times, if you repeat the same process of distillation, then we call it as fractional distillation. Why is it called fractional distillation? The reason is, here you have taken certain amount of liquid with certain impurities, you have condensed it, then again you get the same liquid, but the composition of liquid over here and over here, when you compare, the composition of that particular liquid in which you are interested, that is of more in its fraction rather than over here. For example, now I will put it in this way, you are having a mixture of two liquids. Suppose if this is a mixture of two liquids, instead of one single liquid, it is a mixture of two liquids. For example, like water and ethyl alcohol. If you take a mixture of water and ethyl alcohol, as you know it very well that the boiling point of ethyl alcohol is lesser than the boiling point of water. So, when you start heating a mixture of ethyl alcohol and water, the high boiling water will remain over here and the ethyl alcohol, which is having a lower boiling point, will evaporate first. Then here you will get ethyl alcohol vapors first. Those ethyl alcohol vapors, when you condense, here you will get pure, I do not say pure, but definitely the composition of ethyl alcohol over here is increased. Now, this liquid whatever is formed, if you again repeat the process further, same process if you repeat, then again if you collect another liquid over here, then the third liquid is enriched more in ethyl alcohol. What I mean to say is, suppose if you start here with the 10% ethyl alcohol and if you subject it for the fractional distillation, then the liquid that whatever collect over here, this is again definitely a mixture of ethyl alcohol and water, but here the ethyl alcohol composition fraction is more. Started with 10%, maybe by the time it comes over here, the liquid mixture that you collected over here may be of 20% ethyl alcohol, or even it may be 30%, that depends. This further when you subject it for the distillation again, this fraction if you subject it for distillation again, now the liquid mixture what you contain is further enriched in the ethyl alcohol, now it may increase up to 40% or 50%. Like that the different fractions what you are collecting are repeatedly subjected for the distillation. Then after certain n number of times you will reach a stage where you will collect pure ethyl alcohol. Here let me tell you one thing, that you must be knowing, you must well aware about manufacture of ethyl alcohol from molasses. In the sugar industry we get molasses which is 10% ethyl alcohol. 10% ethyl alcohol solution is present in the mother liquor in the sugar industry. This is what we call molasses. This mother liquor which is 10% ethyl alcohol is subjected for distillation. This is distillation 1. This when it is carried out n number of times, then you will get finally repeated distillation, repeated I will say, repeated distillation when you do, then finally you will arrive at 95.6% of ethyl alcohol is what you will get. From a 10% ethyl alcohol solution from the molasses, by subjecting that liquid mixture, that solution for repeated distillation, that is what the fractional distillation, the fraction of the liquid mixture is collected at each stage and subjected for distillation. Then after n number of steps, what you will get is 95.6% of pure ethyl alcohol. But this is what in fact we call it as rectified spirit. This is rectified spirit. This is even that what we use for medical purpose. This is the rectified spirit. Now, this rectified spirit from 10% to 95.6% of ethyl alcohol you can carry out a distillation, fractional distillation, but 95.6% to 100%, this is what we call absolute alcohol. For this, of course, we do not use fractional distillation, because there it forms an azeotrope. What is an azeotrope? In our previous lectures already we have discussed. Now, what happens in the azeotrope is formed graphically, again we are going to discuss it now, but that we discuss it later. But what you can definitely understand here is that the 10% ethyl alcohol concentration is increased up to 95.6% ethyl alcohol by the process of this fractional distillation. So, fractional distillation is repeated distillation of liquid mixture in order to collect pure component. Now, here what happens when you are repeatedly doing this, here you are the composition of that liquid whose boiling point is less is enriched. Now, in this liquid phase, when more ethyl alcohol is evaporated, so obviously in this residual liquid, the residual liquid is enriched in liquid with high boiling point. In this case it is water. More water is present in this, more ethyl alcohol is present in this. So, finally what we are doing is, because of the difference in the boiling points of the two liquids, we are able to separate out one liquid from the other liquid in a mixture. So, fractional distillation is finally is nothing but a technique based on the difference in the boiling points of the two liquids. From a mixture, the two liquids are separated out. This is the main application, and this is the procedure involved in the concept of the procedure of this fractional distillation. Now, for different kinds of liquid mixtures, how do we carry out this fractional distillation, and what is the result? And another important thing, here I told that because of this because of the distillation, this residual liquid is enriched in more liquid with high boiling point. The liquid that is collected after condensation will be enriched in the liquid with lower boiling point. Now, our next immediate discussion will be what will be the fraction. Suppose if you start with the two fractions, here liquid fraction is Xa and Xb, then from this Xa and Xb, due to evaporation it is changed, the composition, ethyl alcohol is more evaporated. So, this liquid will be enriched in ethyl alcohol. So, here the composition will change, that will be say like Ya and Yb. Then if you are given Xa and Xb, that is the initial composition of the two liquids A and B, then after distillation what will be the composition of those two liquids in the collected liquid A and B, that we have to determine using the values of Xa and Xb, that we are going to discuss now. Consider a mixture of two liquids A and B with mole fractions in liquid phase. Xa and Xb, and their vapor pressures Pa naught and Pb naught. Then from Raoult's law and Dalton's law, Ps is equal to Xa Pa naught plus Xb Pb naught, where Ps is the vapor pressure of the solution obtained upon mixing the two liquids A and B in the mole fractions of X A and X B, right. Now, if the mole fractions of A and B in vapor phase are Y A and Y B, this P S is equal to X A P A naught plus X B P B naught, Y A vapor phase mole fractions are Y A and Y B. Then what also we can say is that P A, that is partial vapor pressure of A in the mixture, is equal to Y A into P S, and P B is equal to Y B into P S. So, from this what we can write is P S is equal to P A by Y A, or Y A is equal to P S by P A. Mole fraction of liquid A in the vapor phase is total vapor pressure of the mixture divided by partial vapor pressure of liquid A in that mixture. Therefore, Y A is equal to X A P A naught plus X B P B naught by X A P A naught. This is straight away, this is another relation. So, if you know the value of X A and X B, and of course, P A and P A naught and P B naught, all these are given values. From this numerically you can calculate if any two liquids are given with certain fractions, and obviously we will be knowing their vapor pressures in pure solvent state, then in a mixture of those two liquids, when they are subjected for distillation, then the fraction of any one liquid, say Y A, will be equal to X A P A naught plus X B P B naught by X A P A naught. Means by knowing the values of X A and X B, P A naught and P B naught, we can calculate the mole fraction of any one of the liquid in vapor phase. Now, this also we can rearrange and certain graph can be made. Consider a mixture of two liquids A and B with mole fractions X A and X B, of course in liquid phase, with their vapor pressures P A naught and P B naught. Then from Raoult's law, for ideal solution, assuming the mixture is a ideal solution, vapor pressure of solution is equal to X A P A naught plus X B P B naught, right. This is vapor pressure of the mixture. Now, in vapor phase, if mole fractions of A and B as Y A and Y B, Y A and Y B are mole fractions of the two liquids A and B in vapor phase. These two are in liquid phase. Now, what relation for Y A we can get it from in terms of X A and P A naught? This, for this what we can write is that from Dalton's law, partial pressure of a gas, in this case say for vapor A, P A is equal to mole fraction of that gas in the mixture, that is Y A, into total pressure of the mixture, that is Y A. So, P A is equal to Y A into P S, right. Now, this P S is equal to X A P A naught plus X B P B naught. So, when you are writing this, now you can write this Y A as equal to P A by P S. This is X A P A naught by X A P A naught plus X B P B naught. Y A is equal to partial pressure of A in the vapor phase divided by total vapor pressure of the solution, which is equal to partial vapor pressure of A is nothing but X A P A naught divided by total vapor pressure of the mixture, that is X A P A naught plus X B P B naught, right. So, from this, the simple thing what is to understand is, if you know the mole fractions of the liquid A and liquids A and B, X A and X B, with respect to their vapor pressures P A naught and P B naught, we can calculate the mole fraction of that liquids A and B in vapor phase at a particular temperature. This is what we can determine. Okay. So, Y A is equal to X A P A naught by X A P A naught plus X B P B naught. Now, this in turn I can write it as Y A is equal to X A P A naught by X A P A naught plus 1 minus X A, because X A plus X B is equal to 1. So, X B is equal to 1 minus X A into P B naught. This in turn I can write it as X A P A naught by X A into P A naught minus P B naught plus P B naught. This is another way of writing, same thing, just we made it. Now, if I reverse this equation, I will get it 1 by Y A is equal to X A into P A naught minus P B naught plus P B naught by X A P A naught. So, this in turn is equal to P A naught minus P B naught by P A naught, because now this X A cancels, plus P B naught by X A P A naught. Now, why I rearranged the equation like this? Because here this type of writing the equation will help us in drawing a particular graph. What kind of graph that we can draw? The graph that what we can draw is, as here it is giving a relation of mole fraction of liquid A in the vapor phase, mole fraction of liquid A in, this is in liquid phase and this is in vapor phase, mole fraction of A in vapor phase to mole fraction of A in liquid phase. So, 1 by Y A versus 1 by, when a graph is drawn for 1 by Y A versus 1 by X A, then you will get a straight line, because then now this is y equal to mx plus c type, where this is the intercept and the slope, this is 1 by Y A versus 1 by X A, 1 by Y A versus 1 by X A, this is y is equal to mx plus c. So, this intercept is equal to P A naught minus Pb naught by Pa naught, and the slope is equal to Pb naught by Pa naught. So, finally the purpose is that if Xa and Ya are known, from the graph you can determine Pa naught and Pb naught can be determined, or if Xa is known and Pa naught and Pb naught are also known, then Ya can be determined. So, from the graph, just if you know the mole fractions in both liquid and vapor phases for one liquid A, obviously when you know the fractions of A, obviously also what you know is the fraction of B. So, when you draw the graph for any one of that liquid, the fractions, then the pure vapor pressures, here now you are getting two equations, right, from the slope as well as from the intercept, you are getting the two relations. So, what you can determine is Pa naught and Pb naught. So, if Xa and Ya are known, you can determine Pa naught, Pb naught. If Xa, Pa naught, Pb naught, all three are known, then what you can determine is the mole fraction in the vapor phase of that two liquids A and B when fractional distillation is carried out, right. So, this is all the mathematics, a little mathematics involved in determining one from the other. After this, what we do now is how to draw a graph for variation in the composition of a liquid A or B in a mixture with variation in temperature. Point is, when you take a mixture of two liquids A and B, and when you subject it for distillation, as you keep on increasing the temperature, the fraction of liquid A or B that is evaporated, that is getting distillated, will be keep changing, right, and the fractions that you collect at different temperatures also will have different compositions of A and B. So, at any given temperature during the fractional distillation, what will be the composition of A and B, or any given composition of liquid Xa and Xb will start boiling at what temperature? This is what we have to understand in our next discussion. Fractional distillation curves. These are the curves that are drawn for variation in fraction of liquids with variation in temperature. Now, again consider two liquids, two liquid mixture A and B with liquid phase composition, liquid phase Xa Xb, vapor phase Ya Yb, vapor pressures Pa naught and Pb naught, pure vapor pressures, boiling point Ta naught and Tb naught. Then the graph is, if you draw vapor pressure or boiling, first let us take both the graphs. This pressure at this end, this Xa is equal to 1, Xb is equal to 0, x b is equal to 1, x a is equal to 0. When the graph is drawn, you will get the graph as like this. These are the two extreme points where this is P A naught and this is P B naught, P A naught and P B naught. This is when the mole fraction of A is 1, B is 0. So, whatever the pressure that you measure, vapor pressure, that will be obviously for vapor pressure of a pure liquid A, this will be the vapor pressure of pure liquid B. As now we are talking about the case of an ideal solution. So, vapor pressure of a solution is equal to x A P A naught plus x B P B naught. That means, vapor pressure of the mixture will lie between the vapor pressures of the two liquids only, right. Now, here you will get two different curves. Now, why we are getting two different curves? The meaning is that the two curves, one curve indicates the fraction of the liquids in liquid phase and one in vapor phase. Again I repeat that the two curves indicate, one is the composition of A and B in liquid phase, one is for composition of A and B in vapor phase. Then which curve is of liquid phase and which curve is of vapor phase? How do we determine? Before that, I will also draw another graph, that is boiling points versus fractions. Now, from this graph, what you can understand is P A naught is greater than P B naught. That means, the boiling point of A will be obviously less than the boiling point of B. So, in that case, the graph will be something like this. This is T A naught and this is T B naught. So, as you have only one liquid A, its boiling point will be something over here. When you have pure liquid B, its boiling point something over here. And when you have a mixture of A and B, the boiling points will lie somewhere between this T A naught and T B naught. Similarly, vapor pressure will lie in between P A naught and P B naught. As the vapor pressure of A is highest, its boiling point will be least. So, you will get the curves like this. Now, again in both the curves, in both the graphs, you will get two different types of curves. As I told, one curve is for liquid phase and one curve is for vapor phase. Then how do we know which is vapor phase and which is liquid phase? For example, in this if you look at it, as the mixture is of liquid mixture is of compositions x A and x B, and boiling point of A is less than the boiling point of B. So, when you start distillation, obviously in the distillate will be rich in the more volatile liquid, that is A, and the residual liquid will be rich in the less boiling B. So, this vapor phase will be rich in A, liquid phase will be rich in B. So, here if you look at it at any particular temperatures, for example, somewhere over here, if you take at this, if you take, then this is according to this curve, this is the fraction of B, and at same temperature this is for B. Now, if you consider this intercept, here x B is less, x A and more. According to our analogy, A will be more in vapor phase. So, this curve will be of vapor, this is of liquid. Again I repeat, if you take the two intercepts at same temperature and the two curves, then on the upper curve the intercept is over here. At this point x A is more and x B is less. So, this is a fraction with A is in more composition than B. A will be in more composition than B in vapor phase, because the boiling point of A is less. The boiling point of A being less, its composition in the vapor will be more. So, on whichever curve composition of A is more at a particular temperature, that will be of vapor. So, this curve will give you vapor, and at same temperature liquid phase composition, if you see, B will be more, because the boiling point of B is less. So, this is how that you have to read the graph. Now, coming to this graph, vapor pressure graph, then here what is happening, that the vapor pressure and boiling point are in inverse relation, as already we have drawn over here. Vapor pressure is high, boiling point will be low. So, with respect to the vapor pressures, when you read, then the reading should be reversed. So, that means whatever here vapor is coming in the upper curve, vapor phase is of the upper curve, and the lower curve indicates the liquid phase. So, here obviously the reading will be different, then the lower curve will be of vapor and upper curve will be of liquid. So, corresponding at the same temperature, correspondingly if the pressure if you do, then you will get the reverse. So, between the pressures if you take, so the corresponding change you can read like this, right. This is how you have to read both the graphs. Furthermore, what we can do is, so this is at a given temperature, what are the compositions you can read. Now, suppose if we have given a particular temperature, at that particular temperature, at what temperature, at that particular composition, at what temperature the mixture will start boiling. Now, suppose if I given this particular temperature, at this particular temperature, the temperature at which the liquid starts boiling is something over here. So, a given composition of a liquid, if it is given, and then at what temperature it will start boiling, then you will measure it like this. So, like this. Now, if this is this particular fraction, if you take this particular composition, then on evaporation this will give you this, then the residual liquid will have certain other composition. The residual liquid will, now the residual liquid will be more in B, that is something like this, then its boiling point will be something like over here. So, like this we can determine that from the graph one can understand that a given composition of two liquids will boil at what temperature, or in the mixture of two liquids at a particular temperature, what will be the fraction of A and B in the liquid phase, what will be the fraction of A and B in the vapor phase, is what we can read from this graphs. Then these are the graphs that we get if we take ideal solution, means where it is the mixture is not violating Raoult's law, where the vapor pressure of the mixture is equal to sum of the partial pressures of the two liquids, that is P s is equal to x A P A naught plus x B P B naught, for that is nothing but, or where the solute does not undergo any association or dissociation, because that is what ideal solution means. Ideal solution means where the solute does not undergo any association or dissociation. They are the solution which follows Raoult's law, or where the vapor pressure of the mixture is equal to sum of the partial vapor pressures of the two liquids. For such kind of ideal solutions, these are the kinds of graphs that we get for the composition of the two liquids, the composition of the two compounds A and B during fractional distillation. Then for non-ideal solution, how do we get it? For a non-ideal solution where P s is either greater than x A P A naught plus x B P B naught or less than x A P A naught plus x B P B naught, already as we told that it will form an azeotropic mixture. In case of azeotropes, how to get, how do we draw these graphs and how do we get it, and what are its consequences, what we can read from that graph, that we discuss next. Curves for non-ideal solutions. In the case of non-ideal solutions, again we have two cases. First, we discuss it for non-ideal solutions with positive deviation. That means, Ps is greater than XA Pa naught plus XP Pb naught. Vapor pressure of the mixture is greater than sum of the partial vapor pressures of the two liquids. In this case, when we draw the graphs, if we consider again the two graphs, that the two extremes, then one for the vapor pressure and one for the boiling point. So, for the vapor pressure again the similar, if you consider that Pa naught is greater than Pb naught case, if you take back again, obviously Ta naught will be less than Tb naught. That means, A is a more volatile liquid than B. Then the graph what we will get is something different from what we have seen over here. It is the positive deviation is what we are talking about. So, here what we get is that the graph will be something like this. These two extremes are of course Pa naught and Pb naught. Vapor pressure of A is greater than vapor pressure of B, like in the previous case what we discussed, and obviously Tb naught will be greater than Ta naught. So, Pa naught is less than Pb naught. So, Ta naught will be, Pa naught is greater than Pb naught, Ta naught will be less than Tb naught. This is Ta naught and this is Tb naught, like this we get. Now, in this again of course, the lower curve will be of vapor phase, the upper curve will be of liquid phase. Now, here it gets reverse, here this will be vapor phase and this will be of liquid phase, right. Like this if you take, now what is actually this points indicates and why we are getting a different type of curve. In the last graph what we got is a continuous decrease or increase, but here it is decreasing and then again it is increasing. The meaning of this is that if you take certain composition of A and B, if you take this is a particular composition, this composition is what we call azeotropic composition. This is azeotropic composition, and in the boiling point case this is azeotropic composition. At this particular composition, the two liquids A and B we are forming azeotrope. Non-ideal solutions with positive deviation will be minimum boiling azeotropes. So, here this is the vapor pressure of the two will be less than the vapor pressures of the two liquids and the boiling point is greater than the boiling points of the two liquids. So, here this is of course with negative deviation, not positive deviation, because the negative deviation means the boiling point negative deviation, non-ideal solutions with negative deviation will form azeotropic mixture of high boiling point, that is what we call maximum boiling azeotrope. Maximum boiling azeotropes are formed by solutions exhibiting negative deviation. Minimum boiling azeotropes are formed by solutions exhibiting positive deviation. So, here in the graph that I have drawn is the boiling point of the mixture is greater than the boiling points of either of the liquids. So, obviously, the vapor pressure of the mixture will be less than the vapor pressures of the two liquids. So, here what is happening is that if you take any composition of in this range, then left side when you move, what you will get is pure A. Right side when you move, you will get azeotrope. Similarly, here left side when you get, you will be getting azeotrope, right side you will get pure B. So, finally the meaning is that any composition of A and B is taken, pure A and B cannot be obtained by fractional distillation. If you take some particular composition over here, left side if you get, you will get pure A, right side you will get azeotrope, but you do not get pure B. But if you take any this composition, then what you can get is right side if you move, then you will get pure B, left side what you will get is azeotrope. So, the meaning is that you are not able to obtain pure A and pure B. Either you will get pure A and azeotrope, or you will get pure B and azeotrope, right. So, and at this particular composition, at formation of azeotrope, the composition in XA is equal to YA and XB is equal to YB. Meaning is that the fraction of A and B in both liquid phase and vapor phase are equal. So, at that particular composition, it is not possible to separate the two liquids A and B. This is what happens in the previous example, what I discussed in the case of ethyl alcohol and water at 95.6%, it will form an azeotrope. From there, it is not possible to get pure A or pure B, that is pure ethyl alcohol or pure water. From 95.6% mixture, if you want to separate, you cannot do it by fractional distillation. You have to do it by chemical method, that is calcium chloride we pass the mixture, water is absorbed, then what you will get is pure ethyl alcohol. So, from rectified spirit, from 10% molasses to obtain 95.6%, that is rectified spirit, what you can use is rectified spirit. But from rectified spirit to absolute alcohol, fractional distillation is not possible, because that is an azeotropic composition. The two liquids cannot be separated. You have to go for a chemical method where we take calcium chloride, water is absorbed, then you will get 100% absolute alcohol, right. This is negative deviation. Next we will see positive deviation also. Now we take the other case, that is solutions with non-ideal solutions with positive deviation. Non-ideal solution with positive deviation means vapor pressure of the solution is less than XA PA naught plus XB PB naught. Non-ideal solutions with positive deviation, they will form minimum boiling azeotrope. Minimum boiling azeotrope means boiling point of mixture is less than boiling point of A or boiling point of B, right. So, again like in the previous case, if you look at the graphs, the discussion is entirely similar. Now, again let us take PA not greater than. So, here what you will get is PA naught, PB naught. This is the azeotropic composition with respect to vapor pressures. And similar boiling point when you draw, then the boiling point of A will be less than the boiling point of B, then the graph will be something like this. This will be T A naught, this will be azeotropic composition, right. So, from these graphs again if you look at it, here if you go in this direction at some particular composition if you take and if you move in the right hand side direction, this is, as I told, this is azeotropic composition. If you are moving in this direction, then what you will get is azeotrope. On the left side if you move, what you will get is pure A. Similarly, if you take this particular composition, then right side if you move you will get pure B, left side what you will get is azeotrope. So, any composition if you take, either you will get pure A and azeotrope, or what you will get is azeotrope and pure B, but definitely again you cannot get both pure A and pure B. This is what azeotrope means. So, for positive deviation, non-ideal solutions with positive deviation means vapor pressure of the solution is greater than XAPA naught plus XPPB naught, then this will form minimum boiling azeotrope. Minimum boiling azeotrope means the boiling point of the azeotrope is less than the boiling point of the two liquids, right. This is what we do it, and these are the kinds of graphs that what we obtain for ideal solution, non-ideal solution with positive deviation, non-ideal solution with negative deviation. With this concept of fractional distillation, azeotropic mixtures, their characteristics, ability of fractional distillation to separate out the liquids, this all the concept is now completed. This Ostwald-Walker method is used to determine vapor pressure of solutions. In this method what it is done is, first a dry air is first passed through an aqueous solution, second then it is passed through pure solvent, and finally into a tube containing calcium chloride. So, here actually that here this is a vessel containing solution, dry air is passed, here you will have a solution, and from this it is passed into another chamber. This is chamber 1. Then the air, after the dry air is passed into the solution, then the same air is then passed through another chamber containing pure solvent, right. From here it is passed into a tube containing calcium chloride. What happens is, when you pass dry air over here, then the air absorbs moisture. So, as a result, weight of air is increased, and this weight, whatever that is increased, is proportional to vapor pressure of solution. when this is directly proportional to vapor pressure of the solution, and further when it is passed over pure solvent, then air gets saturated here with moisture in this. So, further increase in weight, takes place. This if I take it as W1, then W1 is proportional to Ps. This if I take W2, then W2 is proportional to P naught minus Ps. Here this is a solution and these are the vapors. Here the vapor will be less because it is a solution. Vapor pressure of the solution is less than the vapor pressure of the pure solvent. So, to whatever extent the vapors are available, water vapor is available, with that the air gets moistened. Air gets moistened, because of which the weight of the air increases. So, that increase in weight is obviously proportional to the vapor pressure of the solution. Now, when you allow the same air to pass into another chamber where you have pure solvent, then here you will have the vapors, this is P naught, this is Ps. Now, from here to here when it comes, already here certain moisture is being absorbed. Now, here also it will absorb certain amount of moisture, but that amount of moisture is proportional to the difference in the vapor pressures of these two, and here where the air gets more saturated. So, here the difference in weight W2 is, here this W2 is proportional to P naught minus Ps. Finally, when it is passed through the tube containing calcium chloride, now this is wet air, the air completely saturated with water vapor. That wet air is passed over calcium chloride. Here calcium chloride absorbs all the water, all the moisture. So, the total weight, now this is W3 is proportional to P naught, where W3 is equal to W1 plus W2. So, from this, here W1 you are getting, W1 is proportional to Ps, W2 is proportional to P naught minus Ps. So, from this what I can write is W2 by W1 is equal to P naught minus Ps by Ps. For a dilute solution, P naught and Ps if you consider to be the same, then this is equal to mole fraction of solute. So, from this what you can determine is either the mole fraction of the solute, or if the mole fraction of the solute is known and the corresponding changes in the weights if you know, then what you can determine is a mole vapor pressure of the solution. So, here there is a method to determine vapor pressure of the solution. So, vapor pressure of the solution, the ratio of weights of the two, the ratio of increase in weights of the air in the two chambers of pure solvent and solution, W2 by W1 is given by P naught minus Ps by Ps. So, for a given certain amount of solid when you added it, then the corresponding change in the vapor pressure and the decrease in vapor pressure or the vapor pressure of the solution, finally the Ps, because anyhow P naught is a already known value for all solvents, their vapor pressures are known. For that particular solvent, when you add a little amount of solute, how the vapor pressure changes, that you can determine from this equation. So, finally this is a very simple method to determine the vapor pressures of the solutions.